Okay, so let's take off for problems number 6 through, as it turns out, 9. I guess we skipped number 7. So question 6, just kind of hitting this whole idea of particle motion continuously. But if you're going to find, remember, the displacement has nothing to do with when you're going forward and backwards. It's just like, where did you start, where did you end? And so if it's the displacement over these 2 seconds, what I need to do is find out where were you at the end of 2 seconds and subtract where your initial position was. So, of course, if we plug in the number 2 into the original problem, I'm not going to actually show plugging that in, but you guys can do that. If you plug in 2 into the original equation, you get 8. And minus s of 0, which is actually also 8. It means actually you have not actually moved. Wherever you started, you ended up in that same exact place. Now, if you're going to find your average velocity, the average velocity is not instantaneous. It's literally what happened to your change in position over your change in time. And we just found out that we didn't move in that 2-second period of time. So my average velocity would be 0 feet per second. That would be 0 feet. Now, as far as instantaneous velocity, then we are going to have a derivative here. And so v of t would be 9t squared minus 12. And so my instantaneous velocity at 3 would be plugging the number 3 in. Pretty simple little problem. And so I've got 9 times 9, which of course is 81, minus 12, and I got 69 feet per second. And then, of course, acceleration is the next step down, where we're going to go ahead and take the derivative of velocity. So the acceleration would be 18t, and so the acceleration specifically at 4 was 18 times 4, or 72, and that would be feet per second, or I prefer to call it feet per second squared, but some people like it the other way. Now, if you want to know where the particle changes direction, what I need to do is I need to take a look at this velocity graph. And the velocity graph, v of t, which was 9t squared minus 12, I'm going to set that equal to 0, which would be 9t squared is 12, t squared equals 12 over 9. Okay, so if I'm going to put this over here now. So if t squared is 12 over 9, I can reduce that to 4/3, and t would be plus or minus 2 over the square root of 3. Now, we did talk about that, how in calculus, we don't necessarily care if there is a root in the denominator, but I know that at 2 over root 3 and negative 2 over root 3 are the places where the velocity hits 0. And keep in mind the graph of a parabola, this is opening up, so it should be positive to the right and left and negative in the middle, because remember, a parabola with a leading coefficient should go this way, so it should be up on the sides and down in the middle. So you can see that it clearly changes directions at these 2 places. So it changes from positive forward to backwards at negative, and negative to positive. And so I should probably make a little sentence right here. I just didn't leave myself enough room. Just say, hey, the particle moves from forward to backwards at negative 2 over root 3, and from backwards to forwards at positive 2 over root 3. Now, number 8 is actually a pretty simple problem. If the ball is thrown vertically, now notice all of this stuff is kind of sitting here. It's thrown vertically at 180 feet per second. At this, and by the way, I can tell you that actually means somebody was standing on top of a 200-foot high building or object of some sort in order to do that. This 16 here has to do with the gravity. So what is the maximum height of the ball? Well, the maximum height of the ball is going to happen where the derivative equals 0, because of course it's going to go up and it's going to come down. So the velocity is going to be going positive, and then whatever it turns out to be negative, that would be that value. So when I take that derivative, I've got 180 minus 32t. So of course, I want to take this value and I want to set it equal to 0, and that happens at t equals 5.625. If you want to call it 5 5/8, you can do that as well. And then, but that's really not the ending of the story. Is I actually would like to know specifically then what is the actual height at 45/8 or 5.625. And so if I plug that into the original equation, what we get is 706 0.25 feet, or 706 1/4. And again, that's just a case of just doing some arithmetic. Now, number 9 is actually the one that I really wanted to get to on this particular video. This is the setup problem. This is really the one that I wanted to look at. So when you're looking at a derivative that involves logs, the first thing we want to do is actually employ the laws of logs and say that anytime you have a log of a product, you can separate it as 2 separate logarithms with an addition in the middle. And that makes life a lot easier, because now when we take the derivative of a log, and notice this one is a natural log, which is fantastic, you just do 1 over what's inside times the derivative of what's inside. And then over here, 1 over what's inside times the derivative of what's inside. And we're done. That's literally it for 9a. But 9b, we didn't set you up that way. This is the much harder. This is the one we call logarithmic differentiation. There's no log here. The log is simply a tool we're going to use to make the problem get a little bit nicer. So the first thing I would do is take the log of both sides. Now keep in mind that in the rules of logs, exponents become coefficients. Multiplication between things becomes addition. And right here, division is a subtraction. So I've got the natural log of 3x squared plus 3 with a 1/2 in front. Now, keep in mind, I have actually not done any calculus yet. I just took the log of both sides because that allowed me to strip the problem apart and make it look a little bit nicer. Now, that means this one, according to chain rule, is 1 over what's inside times the derivative of what's inside. Again, over here, 1 over what's inside times the derivative of what's inside. 1 over what's inside times the derivative of what's inside. Again, feel very redundant. 1 over what's inside times the derivative of what's inside. So we pretty much have everything done right here. So dy dx is going to be 2 over x plus 2. It's going to be 2 over 2x minus 5. And I can simplify this a little bit because the 2 goes into 6 3 times. And this is what I have on this side. But of course, dy dx is being multiplied by 1 over y. So what I need to do is multiply both sides by y. Now, you could write times y, but that's really not the way we're supposed to finish the problem, because we know that y was this original mess right here. And so that's what we're going to do. We're going to multiply that by all of this ugly, terrible stuff up here. And that is the strategy to use what's called logarithmic differentiation, because the chances that I would pull off a quotient rule together with a product rule, together with a chain rule, all simultaneously is probably not very good. So we rip it apart into little teeny chunks and deal with them one at a time. And that ends problem number 9. And I'll see you back for the last video, maybe next time. Or maybe it's 2. I don't know. We'll find out. Bye.